And then at some point of time, they also found that the superconductor become the perfect diamagnetic, which means that it's repel all the magnetic field outside itself. Actually, we as a human, we are the diamagnetic as well. So if we stand on top of the very, very strong magnetic field, we can float like this as well. The Andre Frank, the Nobel laureate that winning the Nobel from the graphene, right? He also do the experiment with the frog in the very strong magnetic field, and the frog can like float because the living thing is a perfect diamagnetic. No, it's a diamagnetic as well, like superconductors. And you can see this in the internet as well, that the superconductor can float above the magnetic field. Okay, and it's since the discovery, it's been like maybe 100 years, but the transition temperature is very low. It's like maybe at the 2000, it's only 40K, which is the magnesium diboride. At this point of time, we found that this is the superconductor with the transition temperature is just 40K, which is very, very low, because you have to make the nitrogen, liquid nitrogen, and then cool it down to 40K, which is very, very expensive, But sometimes we wish that if the transition temperature is go to the room temperature, it can operate here at this condition, right? And there's some exciting experiment that they add more of the hydrogen into some compound, and you can see that the more hydrogen, the transition temperature increase, right? But anyway, it's come with a price because you need a very, very high pressure to do the synthesis. And this go like 166 gigapascal. This one go to 200 gigapascal and a lot higher, right? Anyway, this graph shows that we have a potential to make room temperature superconductors. But difficulty is that we need a special condition to make it. So there are still some challenging factors that we can discover. And if we have the superconductor, it can make use a lot of everything. You can see that this one is the what we call supercomputer, right? It's a quantum computer that made on the spin instead of the bit that we know. It's called the quantum bit or qubit, everything. So it's fundamentally use the superconductor as well, and some medical devices that use the superconductor. So the application is many applications, right? Anyway, let me talking about the mechanism of the superconductor a little bit. But this is the really, really theoretical things. So I'm going to give you the analogy, right? For example, electron is more like us. If we go into the conference, right? And then we have to talk to a lot of people. So when we travel, sometimes it's very difficult to travel really fast because when you meet people, you have to like interact, right? And then you go someone come to talk to you, so it's very difficult to like travel. But if you come in pair, other people will think that okay, you talk to this one, so they don't come to interact to you much as you just a single person, right? So if you come in pair, the interaction will be less from the outside, right? So you travel easier. And that's the mechanism of the Hubble pairing. So I mean, if the electron going into pair with the help of the phonon, it will move like if there is no interaction between the environment, something like that. You can think of the phonon. Phonon is the vibration in the materials. It's vibrated like this, and then it can quantize to be more like a particle. Okay, and then the phonon can binding the two particles together, and then it's become hardly to interact to the environment, and then it gives you the superconductors. Okay, and how it can be pairing. This is a very, very important mechanism, right? So we're going to talk of it a little bit, right? But I know that you don't like question, so maybe we look at the dancing. Okay, you have the experience of the dancing, right? Especially this kind of dance that you have to dance in pair. Okay, the key of the dancing is that you need to have the right pair. Okay, for example, I asked up here, would you like to dance with me? So he he reluctant. So our pairing is very low, right? So, but if someone would like to dance with me, it means that the pairing interaction is very high. Okay, and also you need the right music as well, because if you find some music like Thai traditional music, it's really slow, and if you listen long enough, you tend to go to sleep. Okay, but if you listen to the Indian music and it's very, very rhythmic, and then you feel like, okay, you cannot keep your legs still. That means that this music induces you to dance. Okay, so in order to have a dance pairing, you need the right pair and you need the right music. Okay, so in terms of the superconductor, we need to calculate what we call the spectral function, right? This spectral function, the vertical axis is how strong the interaction is, and the horizontal is the frequencies. So the interpretation is very easy. So I mean, if you have a peak here, it means that at this frequency, it tends to have you a power of pairing more. But if this in this area the pairing strength is 0, it means that this frequency you cannot pair. Okay, so this picture is more like a music note, of the of some song, of some music, or of some dancing music, something like that. So if you have very strong frequency and strong interaction, it tends to give you the dancing power. Okay. Right. So if we go into the equation, the pairing is we call the lambda. Okay, it's the pairing strength, and the frequency is the frequency average. We call the omega log, which is the frequencies. So and the transition temperature is just the direct proportional to the frequency, and then the exponential of minus 1 over lambda. So with this simple form, you can see that if the frequency is very high, it tends to give you a very high TC, right? Because it seems to be direct proportion to each other, right? And this as well, I mean, if the lambda is go to very large, the exponential of minus 1 over lambda will go to 1. Okay, so in order to keep a high TC, you need to have a high omega log and then high lambda as well. Okay, that's so good. So everybody give a nod to me, so I'm very happy. Thank you very much. Okay, but the thing is that in terms of the experiment, there are a number of ways that you can measure the lambda. We can measure it from the specific heat experiment. We can measure it from the resistivity. But for the omega log, you have no way to do the assessment of it from the experiment. So you have to make some other approximation from the data from the experiment. So the rest of my talk is going to talk about how we can extract the omega log from the experiment. Okay. And the key is the resistivity, because when you raise the temperature above the transition temperature, it go back to the metal state. So it's become a normal metal, which means that you can measure its resistivity you apply the voltage, you measure how much current can flow to the material, okay, and then that's give you the resistivity. And this resistivity is depend on the temperature. Why is depend on the temperature? You can imagine that in the morning, if you go outside the institute, right, and you drive, the road is very empty. You can drive very fast, right? But then, when at the noon, a lot of car on the road, and it give you like a horn, pam, pam, pam. When you drive, you have to drive slower, right? And if you go to the very hot weather, a lot of people come out, and you got a lot of car on the road, and people give you pam, 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 pam. You have to even go slower, right? And maybe you have to change direction a lot, because the temperature is increased. This could be an analogy to this thing as well. So, I mean, when the low temperature, the molecular basis of the material, they vibrate only a little, right? And then they interact with the electron only a little, so the resistivity will be very low. But as the temperature increase, the molecular vibration is stronger, and then it can deflect the movement of the electron more. So the resistivity increase. So from this model, you can see that the resistivity will increase as the temperature increase. So it looks like this. There's someone measure the resistivity from the lanthanum hexahydride, and at the 240 Kelvin. After that, it's become a superconductor. Right? You can see it becomes a superconductor in this area, in this temperature. But if you raise temperature a little bit, it becomes just a normal conductor, and its resistivity is increased with the temperature, like this. It's increased with the temperature. So there are a lot of measurement like this because they discovered the high temperature superconductor. Recently, if you go back to the first slide that I showed you, that there are discovery a lot of this hydride, and it's become a superconductor at a very, very high transition temperature, right? And a lot of them can be measured by experiments. Not just one. I think maybe 10 or 20 of them can be measured by the experiment already. So, so if we go on to the resistivity curve, I just show you a few of them. Okay, and there's a bit of theory as well, because the resistivity can be described very well using a Bob-Grunitzen formula, which is depend on the spectral function that I showed you before. Okay, so if we know the spectral function, we can calculate this one straight away. And at low temperature, it's very messy like this, but at high temperature, the resistivity just linear, dependent of the temperature, like we showed before. Okay, so far so good, is it? And if it is the acoustic phonon, acoustic phonon, right? The part that low frequency, and you can define the speed of sound with that phonon. So the phone itself is mean sound, right? And phonon is mean the quantization of the sound vibration, right? So you got the phonon. If we got the acoustic phonon, the resistivity at low temperature will proportional to the T temperature to the power of 5. Okay, like this. Okay, but as you can see from our spectral function, sorry that this yellow part is the acoustic phonon, which is very, very, very small. The actual or the main contribution is the acoustic phonon, which is the green line here. So if you use that formula, it should be something, doesn't make any sense because the formula is for acoustic phonon. But you can see from this graph that the acoustic phonon is very, very small. The rest of the system is the optical phonon. So I and my students think that maybe we should modify this equation a little bit by using the Einstein model. This one is the Einstein model. So Einstein said that, okay, there are only one important frequency, which we call Einstein frequencies, right? So if we use this spectral function, we put into this the block Grunisen formula. It turns out that you got this equation. Okay, so it might look complicated to you, but let me show you that it can fit to the experiment very well. I extract this from the this experiment. For example, this one is yttrium, deuterium, hexadeuterium. So it's more like a yttrium hydride, but they use deuterium instead of the hydrogen. And this one is a thorium hydride. Okay, so they can measure the resistivity, and you can see that our model, the one that I showed you before, it can fit with the experiment measurement. The experiment measurement is the blue circle, and the model is the red line. Okay, so how much I have? Okay, anyway, it's going to climax already. So, oh, thank you. So I do a lot of fitting to the existing experiment, and it can fit very well. You can see it. Okay, and there is an anatomy of the resistivity. You can see that at low temperature, it's going flat like this, and then at moderate temperature, it's going to be a curve. Dependency, and then it's got the linear as we discussed before. So this is the anatomy of the resistivity. So there are some kind of universality in this resistivity formula, because even you have different compounds, different metal, different composition, all the resistivity look the same. So it must be something that is universal about it. Right? So we do something about our formula and do some transformation. So we find that we have some function that depend on x only. So you put x into this equation, you got some number, right? And you put another x, you got some number. So you can establish the graph that depends on x only, doesn't depend on any system, or any compound, or anything, right? Just put x into it. So you got this function. Okay, I call this one the universal formula. And I apply this to a lot of compounds like calcium, magnesium hydride, thorium hydride, hydrogen sulfide, thorium hydride, and everything. And do transformation to the resistivity data. And all the data can fit into our universal function. All of them. And furthermore, this work just published last month. There is no way that I'm going to know what he's going to publish, right? Just published last month. And they got this, they got this nice curve that have the same anatomy with the one that we discussed before. And this is our universal resistivity. So if it's universal, this graph should be transformed into this graph as well, right? You think, is it? Okay, yeah, I do some transformation this morning, and you can see that our universal function can, luckily, in a very good agreement with the recently discovery, experiment like this. Wow! And okay, let me conclude by this graph, because the parameter in the formula is the Einstein frequency, actually the Einstein temperature. And I also calculate the omega log, and you can see that the Einstein frequency has some strong correlation with the omega log. And as I told you, that the important parameter for the TC is lambda and omega log, right? And the lambda can be extracted from other experiment, but it's very, very difficult to extract the omega log from the experiment. So what I find here is that we find maybe a way to estimate the omega log from the resistivity data. Okay, that should be all for my talk. Actually, I prepare more, but maybe I'll talk later. Okay, maybe next year. If you are interested in my work, this is the open access work. If you read the QR code, it gives you the access to the paper right away. So, I mean, if you take it. So, thank you very much for listening.
This talk is open for questions. Questions? Yes.
So, like at the starting of the presentation, you have shown there is structure function variation with the
Maybe this one.
in the low omega design, that it is basically said that this is due to acoustic phonon modes, and at the high frequency, that is omega A to omega B, it is optical phonon. So how it is reduced? How it is differentiated? That is acoustic and this is optical.
All right. Is it this one?
Yeah.
Oh, this one. Oh, yeah. Actually, we do the DFT calculation, right? And from before we can get the spectral function, we need to calculate the phonon dispersion. And acoustic phonon, you can see that the relation between the frequency and the wavelength is linear proportion to each other, and it defines the sound wave velocity, right? So if that happens, we know that it's acoustic phonon, right? But if the other it gets higher frequency, and the relation between the frequency and the wave vector is different, so we know that it's optical phonon. And special property is that it can be interact with the light. Okay? So that's why we call the optical phonon. And we can do the classification from the phonon dispersion.
Yeah, that's a very good introduction in Charles Crickle. You can look it up. Yeah. Yes, one at the back.
Hello, sir. It was a nice presentation. So I was thinking about this. You talk about the universality of the resistance, and you showed that the function depends on a parameter that is x, which is unique for that particular material. Now, what we can correlate for that means the x will correspond to what property of the material?
Good question. What is the physical interpretation of x?
All right. Yeah, that's a very good question. Oops, sorry. Let me show the equation, right? Actually, it's a scaling of the frequency, because we know that this one is the Einstein frequency, right? And if you multiply by the beta, which is the Boltzmann 1 over Boltzmann and temperature, this one will become the temperature. And this is the normal temperature. So the parameter x is more like a scaling of the temperature. Very good question.
So, and you showed that depending on the pressure, we know that depending on the pressure also, that curve will change, right, with temperature. Means in the second, after this, I think you're having the, yes. Now, within these three data, which one will fit? How do you parameterize that thing?
Okay, I haven't tried the above two. I just tried the last one. But it's possible that there are more complications because if you want to use this formula, you have to make sure that there is a very strong electron-proton interaction. But in the resistivity, it can be a number of things. You can have like something like electron-electron interaction as well, the electron interaction with the grain boundary or something like that. So I mean, if you take a look closer to the data, it's not linear at the high temperature. It's curved a little bit. So if you want to use this one, you have to make sure that the mechanism of the resistivity is the strong electron-proton interaction.
Okay, sir. Thank you, sir.
It's a very good question.
Okay, so let's thank our speaker one more time. And it's time to reward you for the excellent talk.
Please, maybe you take my pictures for you.
Thank you.
Thank you, Professor.
Okay, so we are down to the last talk for this session. So the last talk will be by Dr. Sudhita Roy Barman. And he is going to tell us about exploring nanomaterials on metal surfaces. So Dr. Barman is from UGC DAE Consortium for Scientific Research in Indore. And I will turn it over to him to tell us about exploring nanomaterials on metallic surfaces.
Okay. Am I audible?
Yes, sir.
Great. The title of my talk is Seeing is Believing, Exploring Nanomaterials and Surfaces. I am Sudhita Roy Barman from UGCDA Consortium. While I was making this talk, doing the last things yesterday, I realized that I should change the title. And instead of a colon, I have put a question. And it will be clear why as I go along. And this is our institute. It is a small institute, but it's one of the best places to do honest matter physics research. And we work for different users of universities, and slowly with time we also guide them to some extent. So I would like to thank Professor Anurag Srivastava and the whole team who have worked very hard to make this conference a success. So surface science is basically science of studying two interfaces. That can be solid vacuum interface, that can be solid-solid interface is what these two I will be dealing with. Solid gas, solid liquid are also important. And it is important from many different fields of research and technology. Most important, semiconductor technology and devices, heterogeneous catalysis, where in semiconductor technology we are always looking at the interfaces, building films one over another, and the most important thing is that whether these interfaces are have disorder or they are very good. So this plays a very important role, these interfaces. So what we will be doing in the next 30 minutes, I guess, 25 plus 5, is to introduce. This talk is basically designed for the students. So there will be a lot of interactions and also I hope after the talk and maybe during the talk, and also introduction going back and forth between the different techniques, and ultimately I hope I will be able to arrive at where I want to arrive. So this is BSc or MSc physics. This is a FCC structure, and you can see this is the 1-1-1 surface. If you draw a triangle like this with three corners of the cube, you get the 1-1-1 surface. So now, depending on how we cut the crystal, we get 1-1-1 surface, which is closed packed, We get a 100 surface, which is this surface. Here 110 surface. You can see that these surfaces are different. 111 is closed pack. 110 has kind of chains of rows which are like drains here. So these surfaces are different. So surface science will distinguish between these different surfaces. They have different properties, they have different work functions, and if you look at a surface, it's a zoo of many, many different things. There are clusters, there are vacancies, there is an island, then there is a steppage, there is a kink. So many, many different things which you don't normally think when you make bulk samples, polycrystalline bulk samples. So these are the these different things will have different nearest neighbors. So in principle, their properties can be different, the electronic structure can be different. And so also the surface is like a termination of a bulk. So the surface atoms do not see the atoms in the perpendicular direction. So they can have different extra states which are known as surface states. So with this different techniques using surfaces are XPS, UPS, they are all highly surface sensitive. Most important things required is ultra high vacuum and oriented single crystal. The reason is for ultra high vacuum we need, because the surface has to be clean. If the surface is covered with carbon, oxygen, junk and other things, carbonates, then we don't get the properties. And you can see that only in ultra high vacuum, if we have a mean free path of 5 into 10 to the power 5 for the surrounding molecules, the time to form a monolayer is 10 to the power 4 seconds. So this is a reasonable time in which the clean surface can be measured. In high vacuum, which is normally used, it is in 1 second, you will have a layer formation of other external materials on the surface. But USB is quite difficult because it's a continuous power requirement. The vacuum pumps have to be run 24/7. Cost of equipment runs into many crores. Maintenance requires dedication, experience. Spare parts are very also costly. So you don't find the USB equipment so commonly in our country. Why single crystals? As I have told already, the different cuts look different. So to have these different cuts, we need a single crystal. Then you can cut that single crystal in that particular direction and study that surface. So coming to the techniques that we use, seeing is believing. The most important technique we use is STM in our laboratory. This is the basic details of STM. In STM, one brings a tip very close to the sample, nanometers close to the sample, and measures the tunneling current between. This is the barrier. So the barrier is the difference between the tip and the sample, and the vacuum in between, and we put a bias, and so we have a tunneling. So this tunneling current is very much dependent, very sensitive to the distance between the tip and the sample. So you can imagine the tip has to be extremely flat, mirror polish, and otherwise the tip will go and hit the heliux on the surface and break the tip. And the current has to be measured very accurately. This is called the tunneling current. So this is basically the principle. So this tip is scanning like this here, and as soon as this is a step edge, so this is another set of atoms which is sitting over this set. So as soon as it hits the step edge, the current increases. So there is a feedback loop. The tip goes up, and that is measured as the distance, the Z. Okay. So I'm giving this intro so that at least you look up the internet and find out what I'm talking about. So this I already talked. So these are the different equations which define the current, and if you take a derivative of that, you get a local density of states. So this is the cartoon. The tip comes very close to the sample, and then this is silicon 111, and you can see this is the step. This is one set of atoms. This is another set of atoms. This is a silicon 111 7x7 reconstruction. It's a very easy thing to do in STM. This is all USB STM, by the way. And so this is the atomic resolution image, and you can see these silicon atoms, and this is the way STM helps to determine the surface structure of the 7x7, because the unit cell is 7 times in both directions compared to the bulk silicon, and the structure is much more complicated than the bulk silicon. And so this STM helped to solve this silicon 7x7 structure. In the STS mode, the spectroscopy mode, the feedback is off, and one can get a local density of states. This is the 0 is the Fermi level, always occupied states, unoccupied states, both around the Fermi level. So this was discovered in 1981 by Binning and Roder, and this is their pictures, and this is the first STM they built, and this got Nobel Prize in 86, and this was referred to as a new field opening up the study of structure of matter. This is the machine that we have in our laboratory. There are different equipments. This is where the STM is done actually, and this is the head of the STM, where you can see this is the tip which comes from below, and you can see this is the sample, and this is actually the reflection of the tip on the crystal. So it has to be mirror polished, and the tip comes from below and scans the surface. So some examples. So this is copper 111 surface. You can see the different step edges here. Zoom in, and you can see, take the height profiles and see the heights of these steps, and these are equal to 1 atomic step height. And then if you look at with atomic resolution, you see the copper atoms. These are copper atoms. These are copper atoms here. Take the Fourier transform, you get the information about the reciprocal space also, shows the triangular lattice. This is the STS spectra of copper, and this rising part represents the surface state that copper has, which is very well known from RPET, and also this is the lead. So these are the one example of copper, which is very simple, no reconstruction on the surface. We go to gold. You see, the gold is something when we started the STM in 2010, people said, what is there in gold? So this is there in gold. So they look at the surface of gold. This is supposed to be one flat, close pack. But you can see that there are these wavy things out here, and these are called elbows, and this is called bulged elbow. This is called pinched elbow. So it is a completely different surface reconstruction on gold. It's actually very uncommon for metals. And what happens? This surface reconstruction happens because the top surface is compressed by about 4%, and you can see that in the lower surface there are 22 atoms here. In the top layer there are 23 atoms. So the top surface is squeezed, and that gives rise to these wavy things here. It's called herringbone reconstruction. And if we look at the atomic resolution image, these are all gold atoms, and there are PRLs in the initial days of STM where people, even if they could see any metal atom, it would be a PRL. So, but we are lagging behind anyway, so it went to surface science, but something more was there. But this makes the unit cell so large with this reconstruction, which is 22 cross root 3. Meaning in one direction it is 22 times large, in another direction root 3 times large. And it has FCC, HCP in between, and these regions are called discommunicated. Okay, so, but I didn't tell you something. How do we get this gold surface? Because always there is a native oxide sitting on the gold. And so what we do is that we sputter the sample in situ. The sputtering makes defects. Then we anneal the sample at very high temperature, 400, 500, 600, depending on the sample, and that's how we get a clean surface. So it's not like you get a gold crystal, put it in the chamber, you get this pattern. So the surface has to be cleaned in situ. So this is what I have in the abstract. This is chromium deposited on gold, and you can see beautiful chromium island, the white ones. By the way, these images are all numbers. Okay, these images are all numbers, and this is 512 pixels, 512 pixels. This is 100 nanometer scale. So if I give you a array of numbers of 2,500 or 25,000 numbers, you will not be able to see where is what. The brain very quickly can process the images. So that's why the numbers are plotted as images, and always there is a color scale. Unfortunately, in this one it is not there. Probably in the previous ones were there, but it will come in a moment. The white means this is high, and the brown means this is low. You can see the gold wiggles herringbones below, and these are the chromium. These are the chromium islands, and you can see if I zoom into the red thing, you can see that these are the chromium islands sitting at the bulged elbows of the gold. D is the bulged elbows. It is sitting at these bulged elbows. The reason is that these elbows are more reactive. because there are more gold atoms compressed in that region, and that's why the chromium comes. So these are these, and that template of gold makes them ordered. And there is also these are all atomic step heights, and also there are two types of sizes. One is this small size, and another is this big size. And I will not go into the details because the herringbone reconstruction changes, and because of this change, the second type of smaller chromium islands come up. So this way, using the template of the reconstructed gold, we can make ordered chromium or any other manganese also reported islands, nano islands on the surface. So these are the kind of nanomaterials which are grown in the UHV on a surface. Coming to another example, solid amorphous crystal, there is another type called quasi-crystal. Probably you have read it by now, it's around from the 80s. It has aperiodic long range order, forbidden rotational symmetries. Five-fold, for example. Pentagon normally doesn't occur in the solid crystal structure that you read. Five-fold, ten-fold, these all have, but they have short diffraction patterns. So as an example, Penrose tilings. So you see that these are five-fold. You see there are 5 petals here, and they can fill up the whole space using 2 unit cells compared to 1 unit cell in a normal hexagonal, triangular, etc. like this. Here there are 2 unit cells which are required in a particular way to fill up the whole space. So these are the quasi-crystals, and this is one real quasi-crystal, zinc, manganese, holmium. They are ternary systems. So on these quasi-crystals are basically made of different kinds of building blocks of called Bargmann clusters. They can overlap, and all these are the details of the quasi-crystal bulk structure. I will not go into that, but look into this, that when you cut this, then what the surface looks like. So the surface means you are cutting these spheres or semi-spheres, nearly spheres, and you can see that there are beautiful 5-fold patterns. These are called white flowers. These are called white flower. This is called dark stars, and these patterns are visible because we are cutting through these Bargmann clusters. And if we take a Fourier transform, you see 9 nice quasi-periodic spots of 10-fold symmetry here. And if we take a low energy electron diffraction which studies the surface, we see these 5-fold spots here corresponding to the 5-fold ALPDM surface. So using this as a template, now my example is what happens when you deposit tin. So if you deposit tin, the white ones, so here there is the color scale, you can see these numbers here in picometer, and it's not visible, I am sorry, but the white means it is higher, is that more outside the surface, and black means inside, deeper. And you can see these beautiful starfish-like patterns which actually form on the substrate white flowers, and so we call it SN white flowers. And these are one example zoomed, and then they start to coalesce here. They start to coalesce, and then here at 0.6 monolayer, they form kind of a circular configuration. So these are again the pentagonal nano clusters, you can say. We call it motif, and which forms on the LPDMN substrate and forming these kind of beautiful patterns. So with this, and okay, then we deposit more, it forms 1 monolayer tin, and then we go find the different kind of motifs, and we also find the FFT that is all still there, so it is still quasi-periodic. So, and then we go to deposit a very thick layer, 4 nanometer, still it is quasi-periodic. We see these kind of clusters, and we see the motifs that we saw in 1 monolayer, we see the FFT. So basically, we put deposit tin and form a very thick layer, a pretty thick layer which is not deposited for a long time, So how much time do I have?
5 minutes.
Okay, so that makes it tough because the story has just started. So, but I'll try. Let's pause for a while. The pausing is because Seeing is believing. This was my title. Okay, it's the first part. So, do you believe what I showed you so far? That's my question to you. Yes. I would not have believed because I claim to show you chromium and tin nanoclusters, but there is no evidence that these are chromium and tin. Right? Did I show any evidence? I told I have deposited chromium, I told I have deposited tin. It would have come with some junk on in the USB chamber. Or, no. So, we are a basically experimental group in surface physics, and our bread and butter is photoemission. I'll skip the details of photoemission, but I'll tell you what it gives. It gives you the proof that yes, tin is there on the surface on the tin core level, and aluminium is there on the substrate. And as you deposit tin, as the thickness of tin increases, the aluminium signal goes down and the tin signal comes up. So this proves that it is tin, right? Because we cannot see only with STM and come to conclusions. So I'll come to that in a moment. So, and I'll skip this, that we can also look at with RPS the electronic bands and the bands that you have read in your BSc or MSc in astronomy. So all these bands can be studied. There are equations to find out the momentum, and we move the detector and take data at different momentum and can do it. And the analyzer, which is the detector, has improved over time. And earlier the analyzer was inside the chamber. Now it is outside the chamber, very big. And this is how the measurements are done nowadays. You move the sample. This is the sample. You move the sample in X, Y, Z, and change the angle of the sample. The analyzer is fixed. This is the mouth of the lens system of the analyzer. The electrons are detected at different angles. You can see this angle and measured on a channel plate, and it gives you directly the information of energy versus momentum. The emission angle can be changed into momentum. So this is an example of energy band. This is an experiment, not theory. This is an experiment. You can see all the bands measured here, and with GFT we get an excellent one-to-one agreement. And this is for LTE3. This is a different story, maybe some other time, where we get show that it is a Kremers nodal line metal. So this is the actual talk. In 3 minutes I will finish, because just to give you an idea of what we are doing. So this is tin deposition on a magnetic topological insulator. And this work is published recently. This is the collaboration that we have been doing between myself and Aparna, with your long-term collaborators, and she is my wife. And so this is our latest paper. The experiments were done by Sajal and Pramod, and this is Sajal, this is Pramod in action. The other people are involved. Theory was done by Jagdeep, Aparna student, and Aparna. Styrene I will not introduce. It is like graphene. It is a 2D topological insulator. It has been grown on Bi to T3. The challenge was to grow it on a magnetic topological insulator. So how we do it? Here the cleaning is in a different way. So this is by in situ peeling, and this is the way we deposit tin. This is called a Knudsen cell. This is mounted right here. You can see this yellow thing. This is when it is hot at 800 degrees centigrade inside the USB chamber. And we see with SN deposition these islands growing, and initially the height of the island is too large. It says that this is not tin layer, this is something else, but ultimately we get the heights to be similar to what we expect for a single tin layer, and we get styrene and bi-layer styrene. So now this is again seeing is believing, that we did a detailed analysis of the atomic image. This is the unit set of tin, and the detailed analysis showed us that yes, indeed, we found out the lattice constants and everything, agreement with free standing. So this is one main thing. Then we do also find out the buckling of standing, and we also find out do the XPS. The XPS gives us the detailed information on the standing component, which is SNS, the blue one, and the buffer layer component, which initially forms on the surface. And we do all the core levels, gives us the chemical information. So this XPS is very important for the chemical information. And then we also look at RPS. So these are the different RPS bands. This is with no team deposited as in deposit team. This bulk bands of MBST is SB dope, MN2 BITE4, it goes down, and at this deposition time, 3.6 minutes, you start seeing the standing bands. Now these standing bands, to establish that they are standing bands, we have done DFT, and DFT plays a very important role here. And this is the unoptimized structure. This is the standing. This is the buffer layer of standing, which comprises of 2:1:1, and then we put a standing layer on top of it. And if we do that, we don't get the bands as in the experiment unless we put a hydrogen passivation on top. So after we do that, this is the band that we get. These are all standing PXY related bands. And this is the gamma point, and these agree extremely well with the experimental bands. These are the experimental bands. This is the gamma point. This is this. This is this one, inner hole band. This is the outer hole band. So you get extremely good agreement. And also along this direction here, we could get good agreement. So from that, this is the Fermi surface related to these two bands crossing the Fermi level. So we can conclude that it is steady. So this is the figure which cartoon which says that this is the buffer layer formed because when screen reacts with the tellurium and this one of the NBT surface, after it has reacted, then it forms the starts forming standing. So these are the monolayer standing, and then there is the bilayer standing position on that. So to conclude, seeing is not believing unless seeing critically and logically from all possible angles. So this is the message, and here we have done that to conclude the standing formation happens on NBS. Thank you.
Outstanding talk, very good results. And so let's open this talk for questions. Any questions from that side?
Sir, can we discuss in the duration of the slide?
Yeah, we'll have it in 1 minute. Yeah. Yeah, please.
By transporting this STM and RPS, does the size of the single crystal shape and the thickness of the single crystal matter?
Yes, well, it depends. For STM, because it's a microscopic technique, even if we have millimeter size crystals, it is okay. But less than a millimeter, I mean, half a millimeter, maybe even still okay. But if it is even smaller than that, because we come with the tip from a pretty long distance, so to find the sample may become difficult, but in principle possible. With RPS, it is even more difficult because our spot size is a millimeter in the laboratory. But in the synchrotron centers, you can get micron spot size, so micron samples can be studied.
Okay.
But you have to know the orientation of your sample.
Okay, one last quick question.
Sir, can we calculate the number of layers from height to length cut?
In STM?
Yes.
Yes, of
STM
course.
or AFM?
In STM, that is what the main thing we do. We as soon as we see a step, we measure its height. And we see it is whether it's a single atomic step height or it's a bilayer step height or like that. It can.
Okay, in the interest of time, we'll wrap this up, and we have a small token of appreciation for you, sir. So thank you again for
Thank you.
excellent talk.
Thank you.
So let's thank all the speakers of this session. All the